We're going to talk about ionic bonding and what properties result from ionic bonds. And so the first thing that we have to look at is what an ionic bond is. Once you have a positive and negative ion that have formed, those opposite charges, of course, are going to attract. And that attraction between the cation, which is positive, and the anion, which is negative, is what we actually mean when we talk about an ionic bond. So for example, when you make an Na by giving up an electron and a Cl minus by gaining an electron, then those two are then going to be attracted because they're oppositely charged. Now, what that then forms is a whole big crystal of sodiums and chlorides. It is an important thing to note that an ionic compound's formula is just a reduced ratio of the ions. So the sodiums and chlorides are made in a 1-to-1 ratio, so the formula is NaCl. But you never really have just a single Na paired with a Cl like you would with a molecule. So a molecule, like water, represents a finite unit of the compound. So it is sometimes useful to think about water as existing as a single molecule, although it rarely does too. It's usually in thousands, if not trillions or more. But for water molecules or other molecules, they can actually have a ratio that is not reduced. So for example, butane from like a lighter is C4H10, right, instead of C2H5, which would be the reduced version, because there is a finite molecule that is made up of a chain of 4 carbons surrounded by 10 hydrogens that interacts with other butane molecules, but it's not actually linked to them the way that all the sodiums and chlorides in the sodium chloride crystal are sort of all linked to each other. All right, so what are some ionic properties and where do they come from? First, ionic compounds like table salt have very high melting points. Every single one of them is going to be a solid at room temperature rather than a liquid or a gas. Many of them are at least somewhat soluble in water, so they can be dissolved. What that looks like, the solvation process or the dissolving process, if you have a little crystal of table salt, NaCl, these water molecules have a negative end and a positive end, and they're going to surround the cations, and they're also going to surround the anions. Notice they're surrounding the cations with the oxygen end pointing toward the positive cation, and they're surrounding the chloride, the negative ion, with their positive hydrogen ends being attracted to those negative ions. And pulling apart that crystal is what's happening when you have the dissolving of an ionic compound like table salt. So many of them are able to do that. They're also conductive, so you can actually conduct electricity through any compound that is called an electrolyte, meaning that it has positive and negative ions separately floating around in it, like what we've created up here in our picture of table salt. So if you run an electricity source, whether it's a battery or an outlet from the wall, through a glass of water that's had some salt added to it, you're going to see that the electricity can actually flow. Pure water, which is molecular, that doesn't have any ions added to it, actually is not conductive. But the reason, of course, that we worry about water conducting electricity in, let's say, a lake during a lightning storm, or certainly the ocean during a lightning storm, is because there are ions dissolved in that water. It's very rarely, if ever, pure. So we call those ions electrolytes. So just like in Gatorade or Powerade or whatever, it's when they're talking about electrolytes, they're just saying that there are positive and negative ions floating around in it. Okay, so not all ionic compounds are the same in terms of their ability to dissolve in water and in terms of their melting point. And so we want to talk a little bit about the reasons for that. It comes from something called lattice energy. So lattice energy is simply the energy required to separate a mole of a solid ionic compound into its gaseous ions. It's measured in kilojoules per mole. So what do we mean by that? Well, if I had a big chunk of sodium chloride, let's say that this sodium chloride was much, much larger than this, or let's say you had trillions and trillions of them, until it added up to a mole of sodium chloride. So it would weigh about 58.5 grams. In order for me to pull apart all of these positive and negative ions in this, what we call a crystal lattice, that's why it's referred to as lattice energy, this very organized crystal structure, to pull all those apart from each other so that they are now separate, floating around as gases, would take a lot of energy. Okay, and the energy required to do that is called lattice energy. You can also look at it the other way around, and so I have to put in energy to separate those positive and negative ions that attract each other. Or you could look at it as, okay, well, what if we separated them and then they came back together? Well, they would give off the exact same amount of energy. So you can also think about lattice energy as the energy released as gaseous ions come together to form a mole of solid ionic compound. It would be the same amount both ways, just like, you know, the energy that you put in to raise an object up 10 meters is the same energy that you would get out by dropping it that same distance. They're just equal and opposite processes. So here's some examples of some lattice energies. You know, you can see, you know, kilojoules per mole may not mean a whole lot to you because we really haven't talked about energy a whole lot in this class. But for example, sodium fluoride, you can see, has a lattice energy of about 900 kilojoules per mole. Sodium chloride is smaller. When we have these really big ones over here with like scandium 3 nitride, strontium oxide, we'll talk about why those are so large. But basically what we're just talking about is how much energy, how much heat would I need to pull apart a mole of each of these compounds, or how much energy would be released as they came together. Okay, so here's the same table again. Let's talk about why these numbers are so different, because we have lattice energies that are way, way, way bigger than others. So what are some differences? Well, the mathematical property or concept that's going to sort of tie all this together is called Coulomb's law. Okay, so Coulomb's law basically just says that the force between two particles, in this case we're talking about charged positive and negative ions, is equal to K, which just represents a constant. So we don't really need to worry about that because we're not going to be actually calculating lattice energies right now. But force is equal to this constant times Q1 and Q2 refers to the magnitude of the charges of the ions. So for example, if I were talking about sodium fluoride, Q1 could represent the +1 charge on the sodium, and then Q2 would represent the -1 charge on the fluoride. Okay, so they would have equal and opposite charges, and their charge, the charges are +1 and -1. And then on the bottom we have r squared. Okay, and that just means radius, so it's kind of like the distance between the particles. And the reason it's squared is because radius plays a pretty big part. So as you pull two magnets apart, they don't just gradually go down in attraction, they go down exponentially. And so radius really, really matters. But we can see a couple things here. One is that we can see that the charges are directly proportional to the force. So the bigger the charges, so like +2 and -2 are bigger than +1 and -1 in terms of the difference between them, the greater the force. So bigger charge equals bigger force. We also see that there's an inverse relationship between force and radius. So the bigger the space between the positive and negative ions, so the sodium and the fluoride versus a different, you know, ionic compound, the weaker the force. So as these ions become larger, it actually allows them to be further apart. Okay, so let's take a look at an example here. Let's say we have sodium fluoride. So sodium is +1 and fluoride is -1. Look in the periodic table, we can see that right here. So sodium is a relatively small atom. It does actually get a little bit smaller even by gaining that positive one charge because you're stripping an electron away from its valence shell, dropping it down to a lower valence shell. We're not going to worry too much about that, but just kind of an FYI. And then fluoride is, of course, very small, even though it still has its full second energy level because it's actually gaining an electron. If I compare that to sodium chloride, so the first ion, the sodium, is the same size, but the second one, the chloride, is larger. It's quite a bit larger because it has a whole other energy level added to it compared to fluoride. So because sodium chloride is bigger, that actually puts on average the sodium and chloride ions further apart from each other in the crystal than the sodium fluoride ions. Another way to look at it is you could pack a lot more oppositely charged sodium fluorides into a given space than you could sodium chlorides because the sodium fluorides are a lot smaller. And so putting all that charge really close together, that brings my R down, my radius becomes smaller, and of course it's inversely related to force, so your force becomes greater. So smaller ions actually result in a greater force of attraction, a greater lattice energy. And so if I compare sodium fluoride up here at 910 kilojoules per mole to sodium chloride, you can see that sodium chloride with the larger chloride ion has a lesser lattice energy, meaning that F force between, force of attraction between the two ions is smaller. Now, if I compare that to another relatively small ionic compound, let's go this time with magnesium oxide. And just for the sake of illustration, and also because it is true in reality, magnesium is not a whole lot different than sodium in terms of atomic size. That's true of its ions as well. And oxide is not a whole lot different from fluoride in terms of its size. So this is, in terms of size, you wouldn't expect a big difference in lattice energy between sodium fluoride and magnesium oxide. But if you look at the chart, magnesium oxide has a much, much larger lattice energy, almost 3,800 compared to just 900 for sodium fluoride. And the reason for that is the Q values, the charges. We have +2 and -2, and as a result, those bigger charges are going to attract each other more. And so that's what leads to the greater lattice energy. So the next thing we need to talk about is, okay, if we understand the relationship between charge and lattice energy and between size and lattice energy, we can make a lot of predictions, not only about the lattice energy, but also the properties. So for example, how would you finish this sentence? Melting point. Do you think it's going to be higher if a compound has a higher lattice energy, or do you think it's going to decrease and be lower? Okay, so as lattice energy increases, as we go from, like, let's say sodium fluoride to magnesium oxide to scandium nitride, what do we expect to happen to our melting point? Well, you should, I hope, be thinking that melting point would increase, because if the energy required to pull them apart is greater, then it's going to be harder to melt them. They're going to have to raise them to a much higher temperature. Then the other property that we talk about with ionic compounds that changes with lattice energy, and this is important, this is really important because we'll talk a lot about solubility in the next unit, but how dissolvable or soluble something is does depend on its lattice energy. So what do we think there? Would something become more or less dissolvable or soluble if the lattice energy is high? Okay, so hopefully you're saying that the solubility would be lower, less soluble, if the lattice energy is higher. So as the lattice energy becomes higher, those water molecules that are trying to get in between the ions and pull them apart would have a harder and harder time doing that because the attraction is simply greater.